Good morning, guys. So we will start now. So what we have discussed in our last class, so we have started our discussion on flow between two parallel fixed plates. So let's wait for 1 minute. Okay. Laminar flow between two fixed parallel plates. Now here, so we have written some formulae. Equation number one we have written, and that equation number one we got something. If I'm correct, so please check it out whether we have written this formula or not. This is the formula, we got it. Now I told you we have to integrate two times. So one time, that is dou u by dou y 1 upon mu dou p by dou x into y plus c1. Again u will be 1 upon mu dou p by dou x y square by 2 plus c1 y plus c2. So c1 and c2 we need to get from the boundary conditions. And what is the boundary condition we have? We have a very good boundary condition, that is y is a distance from the bottom plate, Now here plate is not providing any kind of driving force, so we are providing with the help of pump. We have the pump, or we have some other instruments, other some devices by means of which we are sending the water to the pipe. Now here when the flow is happening inside the flow between the two fixed parallel plates, so we have the boundary condition that is at y equal to 0, u is equal to 0 because of the fixed no slip condition, right? We have the boundary condition that is no slip conditions. At again y equal to h, capital H, we have u is equal to 0. Now while putting these two boundary condition, what is the C1 and C2 value you are getting? Tell me. Because both the plates are fixed. So at any cost, no slip condition, as long as the fluid is Newtonian fluids, as long as the we are in a real world, not ideal fluid, not ideal flow. So definitely no slip condition has to satisfy. Now, so when you put those values, you will be getting C1 and C2, and there is no doubt you can get very easily. And I'm directly writing the formula 1 upon 2 mu dou p by dou x hy minus y square. So once again, you are getting the parabolic variations. Once again, what you are getting the parabolic variations. Please try to solve and try to make a habit of solving this uh, partial differential equation, doing the integration of partial differential equation, because nowadays GATE examination they are testing that only, mathematics only. They are not testing whether how much in depth you know the subject knowledge, you have the subject knowledge or not, but they always check for fundamental of mathematics. So try to take this mathematics subject very seriously. Again, I'm saying you may be in a deep trouble when you are start ignoring the mathematics subject. Please try to take it very, very seriously. Now, so here what we are getting the parabolic variations. So we can write parabolic variations. Parabolic variation we can get it like this. Again, how you will get to know that where exactly the u will be maximum? So from the mathematics, du by dy has to be 0 for maxima and minima. What is the tool for us? The tool is the first differential of any variable, any dependent variable has to be equated to 0. So when you equate to that, you will be getting this term. Let's say this is a k, so k times of h minus 2y equal to 0. So y is equal to exactly h by 2. You will be getting the maximum u. That's how you will be getting. Okay. Once it is done, let me know. Please try to do this two steps to get this particular thing. Yeah, it's a very easy one. Just putting the value, getting the solution. C1 and C2. And again, C1, C2, you have to put it into back to this equation. You will be getting the final equation for velocity at any layer at a distance y. Done. All of you have noted down. Now, and we also know that what is the shear stress at any layer y we can get by using the mu times of dou u by dou y, or du by dy we can write like this. And we know the u value as minus 1 upon 2 mu dou p by dou x h by minus y square. So du by dy will be minus 1 upon 2 mu dou p by dou x h minus 2y. So tau will be 1 upon 2 minus dou p by dou x. You will be getting h minus 2y. So what you are observing that it is varying y to the power of 1. So it's a linear variations. So same way as we have discussed in flow between the flow in a pipe, the same cases will be here also for flow between two parallel plates. So it's a velocity variations. This is shear stress distributions. What is the U maximum? At y equal to capital H by 2, we will be getting the maximum value, that is something minus 1 upon 2 mu dou p by dou x h by 2 minus h by 2 whole square, that is equal to minus 1 upon 2 mu dou p by dou x, something like h square by 2 minus h square by 4. So you will be getting minus 1 upon 8 mu dou p by dou x. That will be my u maximum. Done. Done for all. Okay, yes. So here we will try to see the what is the relationship between the u maximum and u average. The same way we have derived for the what we call flow in a pipe. Now, so here what we can have, the flow is happening like this. So here, my dear friend, dq will be what? Dq will be velocity, area of that strip which I am taking at a distance y. Right, I am taking at a distance y some strip So here, let's say the distance from the wall, fixed wall, that is y, and we have the here. So if I take at any layer, it will be dy at a distance y from the fixed plate. So what is the discharge we can get? We can get the discharge formula from where to where? 0 to h, that is dy into 1 into u. Because width I am taking as 1 unit. Width I am taking it as 1 unit. So you know that what is the area? Area will be width into height. Width into height. That is the total area. But elemental area will be what? Elemental area will be dy into width. See, if I integrate from 0 to capital H, I will be getting full-fledged discharge value. Right? So here, what should be the value? dq. If I do the integration, I will be getting q. I can also write area into u average. That can be written as u will be minus 1 upon 2 mu dou q by dou x hy minus y square into dy from 0 to capital H. So here when you do that, you will be getting area. Area can be written as what? Area can be written as capital H into width. Width I am taking as 1 unit, so it is like this. So when you just integrate, after integration, you will be getting u average as 1 minus 1 upon 12 mu h square. So u maximum by u average, you will be getting 3 by 2. Please do that from here to here. A very simple integration. If I do that, I cannot finish the syllabus. Today I need to finish at any cost. So try to cooperate. So here u maximum by u average will be 3 by 2. Now, in a particular, my dear friend, the formula of in between the two fixed parallel plates, if I ask you one question, put a note. The note is exactly, suppose there is a parabolic variations. And I want to get exactly what will be my uniform distributions like this. U average, U maximum. And here, my dear friend, I want to ask you exactly at what distance from the y the velocity profile, actual velocity profile, and average velocity profile cutting each other, or basically intersecting with each others. The same question can be framed for flow in a basically flow in a pipe flow also. So here, what to do that? How to get the value? So you know that U average formula. U average formula is what? 1 upon 12 mu dou p by dou x into capital H square. That is see exactly where they are cutting. So U average equal to U we have to do. Right? Average velocity profile, exactly where it is cutting. It is cutting here. They are intersecting here. So that is what we have to calculate. So here minus 1 upon 12 mu, 2 mu, dou p by dou x, hy minus y square. So this will cancel out. This will also cancel out. So 1 upon 6 h square. Now, so when you solve this equation, you will be getting two values of y. Getting my point? So what we can get from here? Exactly h square minus 6hy plus 6y square equal to 0. Now I need to calculate for y, right, in terms of capital H. So you will be getting what? Two equation. Y you will be getting two value. One is a y1, other is what y2 in terms of capital H. and those two values will be total height is h. So you will be getting two values where exactly they are touching. That can be asked, in gate exam. Till now they have not asked, but that can be asked. Similar is their argument is can be framed for pipe flow also. All of your understanding or not, guys? Yes. Please note down each and everything. Anything can be asked from my notes. Right? I cannot predict actually, but whatever they will be asking, they will be asking from my notes only. Now, once it is done, let me know. And you please try to solve this one as a homework. You see, everything is involving in mathematics. There is a no fluid mechanics without mathematics. In fact, there is a no engineering without mathematics. So please try to start loving the mathematics subject. You cannot hate it. You have to accept the fact that I need to struggle a lot, I need to put a lot of hard work in learning the mathematics, and you please learn very fundamentally these mathematics subjects. Again, I'm telling you, you will get at least 7 to 8 marks ahead of many students just because of the mathematics. If you are not believing, you can just verify it after gate 2024 exam. Once it is done, let me know. Done. Now, so here, my dear friend, we got to know this one. So drop off of pressure for a given length. Drop off of pressure. Similar thing we did for the fluid flow in a pipe. Here also we are doing for the flow between the two parallel plates. This is the capital H we have. This is the length we have. Two section I'm considering. Section 1 from the inlet section, let's say this is x1. Section 2 is there at a distance x2. X2 minus x1, we know capital L, where we are focusing our attention. U average, everybody know that, minus 1 upon 12 mu dou p by dou x into capital H square. So here dou p by dou x will be minus 12 mu u bar by h square into, okay, so that's it. Here we can write whatever the dp is there, dp by dx, so we can write like this, and I can do the integration from 1 to 2. So I will be getting p1 minus p2, that is 12 mu L divided by h square. If I write in terms of head loss, 12 mu u bar L divided by rho g capital H square. There in the fluid flow in a pipe, we got the answer as 32 mu u bar L divided by rho g d square. Here h square, because here characteristic length is what? Capital H. So Reynolds number, if you want to calculate for this case, you have to write rho v average or u average LC divided by mu. So here rho u average capital H divided by mu. Done. So guys, note down the next third case. Third case, we are having cuvette flow. And I told you what is the meaning of cuvette flow? The flow when it happens between the flow when it happens between two parallel plates in which one plate is fixed, another plate and other plates moves. Something like this. So we already discussed this case, but we have discussed simple cuvette flow. We have discussed simple cuvette flow. Here in this case, we are providing pump also plus plate motion also. Both the things are contributing to driving force for a flow to happen, right? Fluid is flowing also because of pump. There is a pump which is being connected, and we have the plate also moving, so both providing extra motion, extra energy to the fluid. So I can divide into two segment. One is just like a two fixed parallel plates where the fluid is being pumped like this, and other case where we have the simple plate, one plate is fixed one and other plate is sorry, one plate is fixed and other plate is what start moving with some velocity u. But let me call this to be capital V here, capital V here. Fluid is at the rest condition. Fluid is not moving. Fluid is just moving because of the plate is moving. We don't have any pump. Here we have pump. Here we do no pump. If I club together, then I will be getting the very special case, that is a case number third. We call that to be cuvette flow, right? Now, so superposition, what is the meaning of superposition principle? Adding together these two conditions to get the condition for what? Third case. Now here I am calling this to be a first and second. What is the formula for the first and second? I will be getting third case. So what is the first formula? First formula, everyone know that. Minus 1 upon 2 mu dou p by dou x hy minus y square if it is capital height. And sir, what is the formula for this case? We know from our basic fluid properties. What is the formula for velocity? What is the formula for the velocity? Tell me, guys. What we can write? Fluid at any layer will move with what velocity? As compared to, let's say, we have the height h and we have the velocity v. So here, what you're understanding, I'm assuming that here to be a linear velocity profile, for example, if I'm assuming here to be a linear velocity profile, so I can write for linear velocity profile for any height h or for any y, what is the fluid velocity? U by v, u by y is equal to v by capital H. So u can be written as v into y by capital H. That is how equal to the velocity profile for a third case. Again, if somebody will be asking you what is the variation, combined variation, it's a parabolic variations like this. Now we cannot say exactly at the middle it will be having the u maximum. For maxima and minima, we have to differentiate and equate to zero. This one. For maxima and minima, this dou u by dou y, we have to equate to zero. So that I will be getting u as u maximum. Right. That can also be the one of the gate question that they can ask. So again, mathematics will involve there. Right. So this is the complete picture of Couette flow. In first chapter, whatever we have discussed, we have neglected this dou p by dou x. That's how we call simple Couette flow. Because we have not taken dou p by dou x value. Now here we have the dou p by dou x because we are providing with the help of pump, as well as we have the driving force with the help of plate. Plate also moving, pump is also there. So both the condition has to be superimposed. Now again, there is a one question you might be asking, sir, if in a problem, if they have not given the linear velocity profile, if they have given the velocity profile to be parabolic, accordingly that this variation will be there, right? That depends on the question to question. For a very general, a very simple case, I have taken this to be a linear velocity profile. Done. Try to solve this question. Consider a laminar flow in the x direction between the two infinite parallel plates, that is a Couette flow. The lower plate is stationary and the upper plate is moving with some velocity 1 centimeter per second in the x directions. The distance between the plate, that is capital H, is 5 mm. The dynamic viscosity is given. If the shear stress on the lower plate is 0, then what is the pressure gradient value? So first of all, we have to understand that it is a Couette flow, not a simple Couette flow. So we have to write complete formula, that is minus 1 upon 2 mu dou p by dou x. This is the formula we have. So here, my dear friend, what we can write, shear stress mu into dou u by dou y. This equal to 0 at y equal to 0. Why? Why it is 0? Because it is given. The shear stress on the lower plate. When y equal to 0, that will denote the lower plate. So minus 1 upon 2 mu dou p by dou x h minus 2y plus v by h. That is equal to 0 simply. And we have to keep y equal to what? 0. So what we will be getting? Minus 1 upon 2 mu that is 0.01, 0.01, 5 into 10 power minus 3 whole square. That is what the values of dou p by dou x. Check it out whether you're getting 2 as answer or not. Are you getting the same? 2. Just check it out. Very quickly, guys. Very quickly. It somewhere we did the mistake. If that is the case, here if we just think of see, I need to multiply with the mu dou u by dou y. That is equal to 0. Okay, so v is what? 0.01. That is also 0.01. So 8. Yeah, so 8 will be correct. Yes. Done. Can I move to the next one? Note down the next chapter, boundary layer approximation. We also say boundary layer theory. BLT. The boundary layer approximation is basically it is bridging the gap between the Euler equation and Navier-Stokes equations, right? Because whenever you have considered fluid flowing over the flat plate, for example, you will see that there is a boundary layer formation is there. This boundary layer formation, inside that we can apply Navier-Stokes, outside that we can apply Euler equations, right? Now, that means it is bridging the gap between the Euler as well as Navier-Stokes equations. It is bridging the gap between the slip condition as well as no slip condition at the wall. Because if you apply Euler equation or Euler equation inside the boundary layer, no slip condition will not be satisfied. Because Euler equation has assumed that we are not considering any viscosity effect, right? So this particular region is what? Highly viscous region. Inviscid region. Why? Because shear force is zero. Why? Dou u by dou y is zero. Now delta is what? Boundary layer thickness. This particular boundary layer thickness, my dear friend, always when we do the experiment, or Blasius did some experiment for the flow over the flat plate, he got the moment we achieve 0.99 times of u infinity, we say that is the edge of the boundary layer. At the edge of the boundary layer, there is a no dou u by dou y, because dou u by dou y is we have calculated from the vertical axis, this theta. This theta will be start decreasing when you see the dou u by dou y graph versus y. Y is nothing but distance from the wall. So what you will be observing that it is keep on decreasing, initially maximum, and it will keep on decreasing. And at the moment when it is delta, that dou u by dou y will become zero, right? The question is, sometimes people used to say 0.99 times of u infinity, that is 99% of the u infinity. We say that is the extent up to which the boundary layer can be grown. Sometimes people used to say 95% of the free stream velocity condition. Sometimes people used to say 96%. Sometimes, see, most of the textbook nowadays, which is going or basically is spreaded in the market, you will see 99% of the free stream velocity. But when you see the research paper or when you see the old books, you will find 95% of the free stream velocity condition also. My question is, will be there any difficulty or any inaccurate solution we will be getting if I assume 95% of the free stream velocity? Free stream velocity is infinity. Once the moment this fluid particle will be start hitting the plate, fixed plate, because of the no slip condition and because of the viscosity, this boundary layer will start growing slowly. The moment it is achieving 99% of the free stream condition, we say that is the edge of the boundary layer. But sometimes people used to say the moment you achieve only 95% of the free stream velocity, then also we are happy with that. So what is the difference between this researcher number one and the researcher number two? Who is more accurate? See, I'm not doing any kind of PhD work here, but whatever the discussion is happening, that they may ask in GATE exam in the form of MSQ. So please try to be very, very attentive what I'm talking about. As I said, my discussion is not valid, and my discussion is not based on the what they have asked in previous year in aerospace or mechanical. My notes and whatever the content is there, I have prepared what's gonna be asked in next year, right? Because you have many sources for solution, for seeing the solution of previous year papers of whatever they ask in GATE examinations, and you will not find this question also, right? Because every year hardly they can put one or two questions from the fluid mechanics or maybe from the boundary layer theory, right? So who knows, the next question will be from the MSQ based on this what I'm discussing right now, that 99% of the free stream or 95% free stream conditions. Will be there any difficulty? The researcher number two is saying no, we have to grow a little bit more to achieve 99% of the free stream conditions. See, the researcher number two who said that 99% of the free stream condition we have to achieve to have more accuracy. If 95%, if I assume that, okay, that is a okay solution. There is a no harm in that solution, right? There is no difficulty with that solution, but still, that is a inaccurate solution as compared to 99% of the free stream conditions. Why? Because in numerical solutions, right, whatever the numerical solution, numerical methods is there, Rangakutta methods, forward method, backward methods, these are giving you the approximate solutions. This approximate solution, see, when you solve any, you have given some project from Government of India that you have to design this something, some example, right? Something you have to design that is being given by Government of India to you. Then what you will do? You will start doing the procedure, and you will definitely come across a condition called boundary layer theory. The moment you will be hitting the fluid mechanics subject or aerodynamic subjects. In that case, my dear friend, what you have to do, if you assume that 95, sir, if I assume 95% of the free stream conditions, that means I'm assuming the boundary layer thickness to be very small. Means that region is very narrow regions. That means indirectly you are assuming the drag force to be very, very small as compared to what the researcher number two has predicted. If the drag force you have calculated less, and by the God grace you are designing the aircraft, let's say for the military purpose, and let's suppose you are landing and you are basically going for the fight with the Pakistan army, right, with that particular aircraft which you have designed with the R1, that means 95% free stream conditions, and you thought that, but while I am moving, like your aircraft is there, that is being suppose it has been taken off, right? And you have assumed that the drag force will be small, so you have kept the not a very good material. Instead of composite material, you have kept some aluminum material, that fuselage part and all, and you thought that drag force is small, so why should I keep it more amount of money in that? And the moment you are about to strike that particular aircraft of opposition, then what will happen? Actual drag force will be more, but you have thought that drag force is very, very small. The moment you are about to hit, you will be gone. The next question, when the inquiry will be kept regarding this all this drama which happened, then definitely who will be blamed first? The engineer who has designed that aircraft. Even though accuracy is not a matter at all, see, 99%, 95%, almost they are same, but still the drag force will might be significant, because in calculation of the drag force we are not only calculating coefficient of drag, CD. See, what is the formula? Half of CD rho a u infinity square. But to achieve at this stage or at this particular calculation, you might have done a lot of other calculation also. Here one assumptions, here one assumptions, one accuracy, two times, three times, four times. That those many small error, they will be accumulated and they will creating a big error, and that big error will be coming in the form of what? Drag force calculations. And if the drag force prediction is wrong, your aircraft will be gone, right? So understanding or not what I'm saying right now? So it depends on whether you are achieving this 99% free stream or 95% free stream condition. That depends on the design criteria which is being given by the customer. Suppose that aircraft is not for the military purpose, right? For the not for the fighting purpose. That is there for some showpiece purpose. In that case, you can take 95% free stream velocity conditions. Indirectly, you are assuming that my boundary layer is a very narrow region. But if you are assuming the 99% free stream condition, that means what? You are assuming the boundary layer is somewhat larger regions. Getting my point? Yes or no, guys? Understanding? Yes. So note down the boundary layer. What is the boundary layer? Or maybe we can have. Note down boundary layer theory. The narrow region forms when the fluid flows over a solid wall. The narrow region forms when the fluid flows over the solid surface. And in this narrow region, the velocity gradient will exist. Right? Put a note: for ideal flow, there will not be any boundary layer. No boundary layer formations. So no slip condition has been violated. No slip condition has been violated. Understanding, all of you. There is a one more term called thermal boundary layer. Anyone aware of that? As it is not that important, but it is important when you do the heat transfer analysis. Whenever the fluid is flowing, which is having a temperature difference, T infinity and the T wall. Let's say T wall is having more temperature than T infinity. Then we form then there is a tendency of formation of what? A thermal boundary layer. Thermal boundary layer is a very narrow region where we say the temperature gradient exists. We denote it by delta T. This temperature gradient will exist, right? Just like what we have the velocity variations, here also temperature variation. Because of the temperature variations, thermal boundary layer will exist. When there is a no temperature difference, when no temperature difference, no thermal boundary layer. Just like for example, we have the plate TW and the fluid TW. No boundary layer. No thermal boundary layer will be there. A very similar concept here also. When there is a no relative velocity concept, when the relative velocity is exactly whatever the plate is being fixed one, but the fluid is not getting the same velocity at the plate, then definitely there will not be any boundary layer formations. So these two question has already been tested in the gate mechanical. This question has been tested, this one, not this one. So this question can be asked, this note. Now, see here, it's a very beautiful example which is given in the Single textbook. See, when you apply Euler equation near to the solid wall, definitely one slip will happen. But Navier-Stokes equation, when you apply, no slip condition will follow. So boundary layer is bridging the gap between C here and here. The meaning is that when you just form the boundary layer, here we have the slip, here we have no slip. Right? Means exactly the moment till the moment of edge of the boundary layer, we have the some what we say, velocity variations. At the edge, we don't have any dou u by dou y, right? So here one picture is there where the fluid is flowing over the flat plate. So exactly when the Reynolds number is 10 to the power 5, we say here, when Reynolds number less than 5 into 10 power 5, we say it's a lambda flow. When Reynolds number is more than 6.5 to 7 into 10 power 5, we say it's a turbulent flow. And this condition is valid for flow over the flat plate. Flow over the flat plate. And as you can see, delta 1 and delta 2. Delta 2 is more than delta 1. Why is it so? In turbulent flow, why there is a, even though there is a high intermixing is there, a lot of momentum transfer is there, but still why it is taking much time to grow or to achieve the condition called free stream condition? Within the shorter span of time, within the shorter span of distance, it is achieving 99% of the free stream conditions, but here it is taking much more distance. Don't you think some contradictory is happening over here? We say turbulent flow, highly intermixing fluids. A lot of mixing is there. A lot of momentum transfer is there. If there is a lot of momentum transfer, then why the hell this fluid is moving in a very, very, basically gaining the velocity at a very, very slow rate? It is just because mixing is a good phenomena, but it is also a bad phenomena. Whatever the momentum transfer is there, momentum transfer obviously will be there between one layer to other fluid layer. Momentum transfer will be there, but whatever the message wall, whatever the messenger is there, viscosity which is being propagating the message from the wall, that will also be rapidly shooting in the y directions among the fluid layers. They will be start communicating with each other fluid layer in each, whatever the ears are there, ears of fluid layer, they will be start saying, hello, I'm being slowed down, I'm being slowed down, and that message will propagate in a larger fluid in the y directions, right? But here what is happening in the laminar flow, they are just moving like this. They are not so much bothering about what is happening with the bottom fluid layer or above fluid layer. Hardly any communication will be there, but still communication will be there because of the property called viscosity, right? This fluid layer will say, I'm being slowed down. Second will say, okay, they will offer some kind of resistance. It will also what, slow down, and slowly they will be start gaining the velocity to something called 99% of the free stream conditions. But in turbulent flow, what is happening? They are not only saying that you why you are getting slowed down, let me just give my momentum to you. So this third layer will transfer the momentum, but the first fluid layer, it is also exchanging with the second fluid layer, and he will say, how can we move forward? First of all, a lot of mutual understanding is there between us, right? A lot of momentum transfer is there between us in turbulent flow. And whenever we have the lot of mutual respect or mutual understanding, or maybe we have a lot of here momentum exchange is happening, then I have one more problem with us. Because of momentum transfer here, in the turbulent flow, not only we have only one wall shear stress, whatever the shear stress is there, which is being there because of what, viscosity. But here we have, because of the momentum transfer, because they will be start hitting the molecules, right, mixing with the molecules, some molecules which is being badly slowed down, which is badly affected by the plate, this fixed plate, that will also transfer momentum to other fluid layer, right? Right now, this fluid layer which is being attached in a laminar flow, nobody bother about that one. This particular fluid layer, this black color, nobody bother about that because they are moving in a very laminar fashion, parallel fashion. But here, a lot of momentum transfer is happening. This fluid particle will be start what? Exchanging the momentums. And while exchanging the momentum, you know that in exchanging of momentum, we have one more viscosity that is called ED viscosity, or we also call turbulence air stress. That will also hampering the uh, what we call situation of being improvement, that is in the y direction. We know that fluid velocity will be start gaining, each and every fluid layer will be start gaining the fluid velocity, but because of the ed viscosity, because of the turbulent viscosity, right, the bad impact of momentum exchange will also be contributing of getting what, slow down this delta 2, means it is taking much distance to achieve 99% of the free stream conditions as compared to the laminar flow. All of you are understanding what I'm saying? In laminar flow there is only one way of stopping the molecules, that is viscosity, but here we have two way of stopping the molecules, that is ed viscosity as well as what, fluid viscosity. Getting my point, all of you? So if somebody will be asking you why delta 2, why delta of turbulent is much more than laminar, then you have to explain. That is the one question. Second question, in the laminar flow you will observe this is the growth of the boundary layer, for example, but in the turbulent flow you have much flatter curve. This is for turbulent, this is for lambda. Now you try to focus your attention here, near to the wall. When you focus your attention near to the wall, what is happening? A very good thing is happening. In the turbulent flow, it is much flatter curve as compared to this laminar. Why there is a flattering is there? Because of a good effect of momentum exchange. Fluid will be gaining the momentum. This second fluid layer will be gaining the momentum, right? As compared to the first fluid layer, third fluid layer. This second fluid layer is gaining the momentum from the third fluid layer, above fluid layer. What? Because of the momentum exchange in the turbulent flow. In laminar, that much of momentum exchange is not happening. So that much of fluid viscosity, fluid velocity cannot be imparted to the second fluid layer. Getting my point, all of you? Whether these two questions has been clear? Why it is a flatter curve? Why delta is larger in turbulent flow as compared to the laminar flow? Getting my point? This is of no use. Just forget about transitional flow. It's just there for the showpiece purpose. I will discuss when we discuss little bit more about this detailing of turbulent velocity profile. I think I already discussed in the uh, there is a back session of 24 minutes or 30 minutes, right? What we did. Now, note down the next concept: displacement thickness. Here, basically, you try to remember it is viscosity which is happening because of the momentum exchange, right? A lot of momentum exchange are happening in the turbulent flow. Momentum exchange, it doesn't mean that from a higher fluid layer to the lower fluid layer. It can happen from the lower fluid layer to the higher fluid layer also. And below any fluid layer, we have bad fluid layers, which is badly impacted by the, which is badly slowed down by the effect of wall. Wall is fixed wall, right? So that also being transported to the second fluid layer, and above that we have the higher velocity fluid layer that is also being impacted because of the property called viscosity. That is a fluid property, but flow property, because of that ed viscosity is being getting generated because of the bad impact of, because of the bad impression of what we call momentum exchange in the turbulent flow. In laminar, it doesn't happen. Laminar flow, they are flowing in a parallel manner, but in a turbulent flow you will see after a certain point of time lot of intermixing. So displacement thickness, that is a very important thing, and why we need that thickness, that is also one of the important question. A displacement thickness is the distance that a streamline just outside the boundary layer is being deflected away from the wall due to the effect of boundary layer. Now, so note down one more definition, or it is defined as a distance measured perpendicular to the boundary layer of solid wall, by which boundary should be displaced to compensate for the reduction in the mass flow rate. Mass flow rate because of formation of boundary layer. Now this definition will be clear after my explanation, and this explanation will also be get clear after my explanations. Now for that I need to explain you a little bit some concept. Now all of you have noted down. It's one of the some of you might be knowing about this concept, but it is one of the very important concept. You can note down the formula also. Displacement thickness, you can write capital U as U infinity. And what is the small u? Velocity of any fluid layer at a distance y from the fixed wall. Now, is it done? Now, guys, try understanding. Whenever we have the flow over the flat plate, whenever we have the flow over the flat plate, all are moving with the same free stream conditions like this. The moment they will be start heating, there will be some boundary layer formation. Yes or no, guys? There will be something called boundary layer formation, and that will be keep on growing like this. Agree with me? Tell me, guys. Let's say here to here we are considering delta. For example, delta is a distance measured perpendicular to the flow directions, that is called boundary layer thickness. Tell me, guys, whether this is clear till now. What is the mass flow rate at this point? Point number one, and let me consider here to be point number two. Mass flow rate at section one. What is the mass flow rate? Rho into area into velocity. We can also write rho into area. Area is what? What is the area of the flow? Area of the flow can be written as, see, this is my perpendicular directions. This perpendicular direction I can write width as 1 unit. 1 unit, right? 1 into what? Delta. Into velocity will be u infinity. So rho into u infinity into delta, that is my mass flow rate at section 1. Now let me consider here profile to be a linear velocity profile. For example, I'm assuming here the velocity profile to be a linear velocity profile. For the sake of simplicity, now you tell me at any layer, let's say here it is u infinity, at any layer, my velocity of the fluid will be u. Once it has the linear velocity profile at a distance delta, and I want to calculate u at a distance y, then what will be the relationship? U by y, u infinity by delta. So u is equal to u infinity into y by delta. What is the mass flow rate at section 2.2? We have to do the integration because velocity profile is not a fixed one. It is varying with respect to y. If it is varying with respect to y, we have to perform some integration. And what is the integration? Rho into, I'm just assuming one small thickness dy. I'm assuming one small thickness dy here. So if I just do rho into dy into 1, why dy into 1? See, this is a dy. Through this, whatever the flow is happening, through this particular what we call dy into 1, through this area, whatever the flow is happening, my different, I'm assuming that flow to be u into dy into 1. And if I integrate it from 0 to delta, I will be getting complete picture of what we call mass flow rate. So what I can write, 0 to delta, rho into u is equal to what? U infinity into y by delta into dy. So rho into u infinity by delta into y square by 2, that means delta by 2. So what I'm getting, rho into u infinity into delta by 2. Now tell me what is the mass flow rate at section 2. Mass flow rate 1 divided by 2. So what is the mass flow rate? What is the remaining mass flow rate? Where it is gone? According to fluid mechanics, mass has to be conserved. But on the account of boundary layer formations, you are getting surprisingly, you are getting the reduced mass flow rate. Then where the exact half mass flow rate is gone. Now, to basically get the remaining mass flow rate, it cannot go anywhere, right? So something in some other directions it has to go. Then from where it will go, it will be start flowing in these directions, remaining mass flow rates. Some mass flow rate will be flowing here, and some mass flow rate will be getting the area from here to here. So they will be start flowing in these directions. Due to that reason, we are getting shifting in the velocity streamlines, something like this. Before getting the boundary layer formations, streamlines are parallel with each other. The moment boundary layer which is being formed, because of that formation of the boundary layer, the streamlines is getting what? Shifted like this. It will no longer will be parallel. Due to that reason also, to achieve the same free stream velocity, see, let's say this is a u infinity. To achieve that same free stream velocity, it has to travel more distance. See that. As we march along the plate, to achieve the same free stream condition, delta 2 has to be more than delta 1 because of shifting of the streamline, right? Because initially, whatever the boundary layer formation is there, my dear friend, it was the flow rate something like this, parallel. But after certain point of time, the flow has to be shifted. It was parallel, and now suddenly it got shifted like this. Why it is being shifted like this? Because to satisfy the mass flow rate conditions, some more area we need to provide so that the mass flow rate can be conserved. Now let's see how the mass flow rate can be conserved. All of you have noted on this one? All of you have noted down? Is it done? Now what I'm saying, because of to satisfy the mass flow rate conservations, what will be there? Streamlines will be getting shifted. The streamlines are getting shifted like this, and it is being provided here to here. let's say above the boundary layer, we know that the fluid will flow with the same uniform velocity. Now, my dear friend, here this is delta, right? Let me call this height to be some name. The name is, let's say some jet, for example. I don't know what is jet. Because of the flow pattern which is got shifted like this, it is being shifted in the upward directions like this, upward direction like this, right? It is indicating that the flow try to shift in the upward directions. Why? Because there is some mass has been reduced. To satisfy further mass conservation, it has to what? It has to flow in the upward directions, not in the downward directions. Now, the good question is what to do with that. Initially at section 1, you have u infinity. At section 2, I can write mass flow rate exactly has to be equal to mass flow rate at section 2. But what is the mass flow rate at section 1? Can we write rho into u infinity into delta into 1? Width I am writing as 1. Mass flow rate at section 2 can be written as 0 to delta rho into dy into 1 into u plus delta 2 delta plus z rho into what we can write? Rho into u infinity into dy. Can we write like this? Because above that, the fluid layer will start moving with the free stream conditions outside the boundary layer. This is what we have, boundary layer. Outside the boundary layer, we know that it is going to flow with the actual free stream conditions. It is going to flow with the actual free stream condition, my different. So what we can write here? We can write comfortably. Further, we can write this as 0 to delta rho into u infinity into dy. Any problem? Check it out. Anyway, if you just do the integration, rho into u infinity will outside, dy integration will be y, and y, if we put the limit delta to 0, you will be getting rho into u infinity into delta. Then what you can write? Rho into dy. Here I can just ignore rho. Rho will cancel out from all these both sides. So here we can write delta 2 delta plus z, something like this. So here, my different, what you are getting. Can we write this particular term as u infinity into z? Check it out. Tell me guys, can we write like this? Yes or no guys? I don't know whether you're understanding or not. Tell me guys. Yes, totally blank faces I can see. See, when you do the integration, I will be getting u infinity into dy delta to delta plus z. I will be getting u infinity into y delta to delta plus z. I will be getting u infinity into what? Z only, right? So what we can write further? We can write further as 0 to delta u infinity minus u into dy. That is u infinity into z. Then what we can write? U infinity minus u into by u into dy u infinity from 0 to delta. Then what we can write? 0 to delta 1 minus u by u infinity into dy. And what is this z? Displacement thickness. So here, my dear friend, we cannot provide, because yeah, just now what we have seen in our example, we have seen that the mass flow rate is what? Being reduced. The mass flow rate is being reduced by half. When the mass flow rate is being reduced, right? So what I can do, if mass flow rate has been reduced, how the mass flow rate can be increased? Rho into a into u infinity. See, I cannot increase rho, I cannot increase u infinity. All I can do with my best effort, I can provide some extra area. If I can provide some extra area at section 2, definitely I can increase my mass flow rate so that it can match with the total mass flow rate at section 1. And that is why, my dear friend, we are providing extra area in terms of extra area, delta star into width. That is the extra area we are providing to compensate for reduction in mass flow rate, or we say to basically to satisfy the mass conservation, we have to provide some extra area, some extra thickness. That is called displacement thickness. Make a note of it. It's our hypothetical thinking. See, again, you will ask me, sir, do these things, whatever you are explaining, do these particular things are actually exist? See, actually, existence of flow will be something like this only. So flow will be start shifting like this. So can't you imagine that it is providing some extra area? The moment they will be start flowing like this, let me just show. See here, when the flow will be start taking place like this. So don't you think it is it is indirectly providing some extra area like this? We are concentrating our focus at section 2. It is just assumption that we are providing some extra thickness, that is a delta star, so that mass flow rate can be increased. But in reality, they will be start flowing in this way, like this. It will not flow like this. Means whatever the boundary layer is there, it will not flow like this. If it is start flowing like this, it cannot provide some extra area. It cannot provide some extra area, right? So to satisfy the mass conservation, it will be start flowing like this also, and it will start flowing. See, it will be start flowing like this, and it will be start flowing like this also. So it has both the component u as well as a small v, so that the resultant velocity will be like this. And you know that, and everyone know that. If I draw the tangent to the streamline, I will be getting what? The velocity, resultant velocity directions. So that's why we say boundary layer flow is a 2D phenomena, 2D flow. We got both u as well as v, but v is a very, very small. V is a very, very small, right? Remember, if you are thinking that streamlines should be parallel, then it will be getting only u component, no v component. If no v component, then how it can flow like this? How the mass flow rate can be conserved? How the mass conservation can be there, right? So those are all these things are there. If for the more flow visualization, you please watch YouTube videos, some animations. You will get the ideas. How in actual condition, if you see the simulation also, right, in ANSYS Fluent, you will get to know how the flow is getting deflected. Now, then all of you have noted down. Done. Tell me, guys, very quickly. So now you can read the statement, both the statement, and you can easily digest both the definition of displacement thickness. Displacement thickness is the distance that a streamline just outside the boundary layer is deflected away from the wall due to the effect of boundary layer, and it is also defined as the distance measured perpendicular to the boundary layer, boundary of the solid wall, by which the boundary should be displaced to compensate for the reduction in the mass flow rate because of the formation of boundary layer. Now, now, so when you try to see this question, what is actually happening? The velocity profile in an incompressible laminar boundary layer is shown in the figure. U is nothing but the free stream velocity, U infinity, you can assume. U of y is the stream-wise velocity component. The area of the black shaded region will denote what? The area of the black shaded region in the figure so below representing what? This one, whatever you are seeing the black color portions, they are asking that one. This is nothing but missing flow. What is the meaning of missing flow? Full velocity is not there in this area. Area is available. See, area is, see, what is the, why mass flow rate is getting reduced? Rho into u into area. Area is available. Nobody can deny from the fact. Whole area is available for the flow. See, if I show you what actually happened. Here also area is what? Delta into 1. Here also area is what? Delta into 1. So nobody can take the area. But actual reduction is happening in the mass flow rate just because of what? Velocity. So full velocity is not there in this area. That's why mass flow rate reduced inside the boundary layer. When the mass flow rate is getting reduced inside the boundary layer, then we need to provide some extra thickness in the form of displacement thickness. So the area which is being shadowed in the region will represent what? Indirectly, displacement thickness only. This only area, whatever the area which is being not occupied by the velocity profile, this area which is not been occupied, this extra area I'm providing what? Here. Understanding? Displacement thickness into width. Width they are taking as 1 unit. So we can write area which is being deficit area, right? Or basically the mass flow rate which is being deficited because of what? This displacement thickness only. So what is the reduction in the mass flow rate? If somebody will be asking you, what you can write? Rho into U infinity into delta star into width. Done? Now, try to solve this question. Consider a study two-dimensional. See, why it is mentioned two-dimensional? Because I told you, U and V component both exist. Flow over the non-porous flat plate as shown in the figure. For a control volume PQRS, the speed is U infinity at the section PQ is uniform. That means the flow is what? Uniform over here. The moment they will be start hitting the plate. And they are asking at RS section, the velocity profile is given something like this. The value of A naught for which the flow through section PS will vanish. That means there is a no flow here. We know that mass flow rate PQ is equal to what? Mass flow rate at RS plus mass flow rate in RS in PS. That is the mass conservations, right? I told you, right? In reality, the mass flow rate is being compensated by providing some extra area or the flow to be happen in this PS region. But now it is being cut off. It is zero. So now this mass flow rate has to be equal to inlet mass flow rate and whatever the mass flow rate which is being passing through RS section. Now, so mass flow rate at PQ, everyone know that rho into U infinity into H. And what is the mass flow rate which is being there through RS section? We have to perform the integrations. What is that? 0 to H rho into dy into 1 into U. But U is given as something like this. So rho into U infinity into H rho into A naught into y to the power n h to the power n into dy. So when you calculate, you will be getting the answer as so U infinity into h, that is equal to A naught sorry, this will be h only. A naught will be U infinity into L plus 1. B will be correct. So we are satisfying the A naught in such a way that still the mass flow rate will be conserved. So this question they ask in GATE 2022, right? From where they have taken this question? Directly from mechanical. See that. I will just give some time for noting down this question, but just for a moment, you see this question. I study laminar boundary layer, which is being flowing over the flat plate. The free stream velocity condition is what? U naught. The velocity profile at the inlet is uniform, fixed is there, but at the downstream at CD location, the velocity profile is varying as a parabolic. The mass flow rate through section BD will be what? So again, mass flow rate through section AB equal to mass flow rate through section BD plus mass flow rate through section CD. That we have to do. Same motivation, same question, but they have just given the flow rate through PS section will be vanished. But the equation will remain same. Make a note of it. So that's why it is being advised multiple times to try to solve other branches question and take it very seriously. Not just solving. Note down each and every other branches question which are relevant to your, which are there in your syllabus. You please make a note of it, that question also. So always you revise your notes, you revise that question also. Because you will assume that that is they are asking in different branch, then that particular question is very tough. They cannot even ask in aerospace. That's the mentality of the many students. And the moment the question will be coming, then gone. Highly unpredictable exam, but still you can make it very predictable when you follow very seriously each and every topic of the syllabus which is being mentioned. So I'll be extending the class for more than 1.5 hours today. So I'll be giving the break after 12. Then again you have to come back because there is no other class, right? Today you don't have any other class. Now I think this question is over. You just take a picture of this and try to solve as a homework. Nothing we have to do, nothing, because only we have to calculate mass flow rate through section CD, rho into, just take the elemental area through which the flow is happening, and you try to integrate from where to where, 0 to delta, 0 rho into dy into u. And what is the u value? 2 into y by delta minus y by delta whole square into u naught. Once you are able to do the integration, you have to keep it, and you know mass flow rate through AB section, that is rho into u naught into delta into 1. Done? All of you done with this? This is a reality, and what we have discussed, that is the imaginary concept, providing some extra area in the form of displacement thickness. Now, note down the momentum thickness. Now, momentum cannot be conserved. Momentum cannot be conserved, unlike what we have seen the mass flow rate, which is being conserved. Now, when momentum cannot be conserved, initial momentum minus final momentum will give some forces. That forces will be called here drag force. Unlike your thrust force, which is being imposed in aircraft or maybe missile or rocket. There also momentum changes are happening, right? What we used to write, thrust power or thrust force, what we used to write, mass flow rate, VE, that is VA, plus, tell me guys, some other term is also there, or is it sufficient? Will this will be sufficient to provide the thrust force? Perfect. PE minus PA into, correct. This term will also be there. Area at the exit, that will also be there. So just like here, my dear friend, you have the initial momentum and final momentum that will give rise to some thrust force, and that's how your rocket or missile is being flying, or maybe they have been launched. But here, what is happening in case of fluid flow, when the momentum changes will be there, that will give me not the thrust force, that will give you drag force. Note on the formula. Momentum thickness is defined as the loss of momentum flux, the loss of the momentum flux per unit width divided by rho u infinity square due to the presence of growing boundary layer. Now, the moment I will derive this picture and this picture will get clarified. For that, you need to wait. So drag force can be written as from here to here, rho into, see what are the force formula? Force formula, mass flow rate u into mass flow rate into u. Mass flow rate is what? Rho into u infinity square into what? Area. Area is what? Thickness. That is momentum thickness into 1 into u infinity. And that's how you are getting rho into u infinity square into theta into 1. That is the drag force. Area in terms of area, you can write theta into 1. Width is 1. Unit width. Now, guys, you can note down one more definition regarding this. Or it's better that we just write here. Now, my dear friend, here momentum will be decreasing or increasing? Tell me, guys. Momentum of the fluid will be decreasing or increasing as it is marching along the flat plate. What is the momentum? Mass flow rate into U. We know that when the boundary layer will form, mass flow rate will reduce. Momentum will also be reduced. Right? And this initial momentum minus final momentum will give me the drag force. Let's see how this formula has been derived. For that, just wait. Now, all of you have noted down, so note down. Initial, I know I told you, right? What I told you, that we have the boundary layer formations like this, and we have seen that here some extra area is provided in the form of delta star. Delta. See, guys, I believe that even though we have the time constraint, so but still, uh, I will not be basically giving any excuse to skip these derivations, because derivations, again I'm saying, you will help you in getting or attacking a very good level questions. Believe me. So mass flow rate at section 1 and 2 has to be conserved. Now, what is the momentum at 1? What is the momentum flow rate? What is the momentum? What is the momentum rate at 1? Can we say rho into, what is the momentum formula? Momentum formula, we know that mass flow rate into velocity. Here mass flow rate is what? Rho into u infinity into delta into 1 into u infinity. So what we can write, my different? We can comfortably write rho into u infinity square into delta. No problem at all. What is the momentum at section 2 2? At section 2 2, we have two momentum. First is rho into integration of rho into u square into dy into 1 from 0 to delta, plus we have another momentum, that is rho into u infinity square into delta star. Any problem? Width is 1 unit. Check it out. Any difficulty? No. What is the momentum 1 minus momentum 2? So we can write, my dear friend, here rho I can take outside, u infinity square into delta, this particular term, minus rho I have taken outside, so u square into dy 0 to delta, minus here rho I have taken outside, so here we can write further as what we can write. Okay, so here I can write u infinity square. What is the delta star? 0 to delta 1 minus u by u infinity into dy. Can we write like this? So 1 minus u by u infinity into dy from 0 to delta. No problem at all. Tell me, guys, any problem? Further, what we can write? U infinity square into delta minus. So what I can do, I can just club this together, these two terms. U infinity square minus u square into dy. Just wait. See, once you know the fundamental thing, the derivation seems to be very, very easy for you. Here I can write this term as u infinity square 0 to delta u infinity minus u by u infinity into dy. One term will cancel out, so I'll be getting u infinity into mm, Okay, just wait. Here some mistake is there. No. Here, my dear friend, you have to do the integration. And u infinity into what you can write. U infinity minus u into dy. So any term is cancelling, just please check it out. Whole bracket. So rho into minus of u infinity square into dy from 0 to delta plus u infinity into u dy 0 to delta. So this will cancel out. So I'll be left with which term? I'll be left with 0 to delta u into u minus u square into dy. Further, what I can write, my dear friend? Here we can write momentum 1 minus momentum 2. U infinity into u minus u square into dy. What you can just take? You can take u infinity square outside. You can divide and multiply with the u infinity square. So here you can write u by u infinity minus u by u infinity whole square into dy. Further, we can write u by u infinity like this, 0 to delta. That is what you have the drag force. So drag force per unit rho u infinity square, you will be getting what? U by u infinity 0 to delta. And what is this? What is this particular term? What is this particular term, my dear friend? See, momentum thickness. This particular term is thickness. So what I can write? Drag force rho into u infinity square into theta. Getting my point or not? I have just carried down the same definitions of what we have defined the momentum displacement thickness. From there on, I am carrying this one. Some little bit of mathematics is required in between that, and after that, you will land up getting the same formula. Everyone clear with this? Please check it out. See, I'm not doing derivation for my purpose. If it is not clear, please say yes or no. Tell me, guys. I'm just doing, if at all one student is also benefiting from my particular derivations, then I'll be very happy. I just want to show that how actually we are getting initial momentum minus final momentum, how we are getting the drag force. If it is now, you only tell me whether it is getting zero. Tell me here. Here, whatever we have done, momentum 1 minus momentum 2, whether it is being getting zero, this quantity is zero or non-zero. Tell me, guys. You only tell me whether this u infinity into u minus u square integration dy, whether this term is zero or non-zero. It's a non-zero. When it is a non-zero, then can you say very confidently that momentum cannot be conserved, unlike mass which is being conserved? Yes. Getting my point? So here, momentum, we cannot say momentum is conserved because we have some extra non-zero that is not equal to zero. So definitely, if momentum is not conserved, If any momentum difference is there, that momentum difference according to Newton's second law, right? Nobody can deny from the fact that Newton's second law is being exist, and who said very clearly, whenever there is a momentum exchange is there, whenever there is a momentum difference is there, higher, lower, lower, higher, it will give some force, and that force will be the drag force, right? Now, is it done for all? Now, so here, my dear friend, we will discuss few more things regarding this boundary layer. So here, what I have done till now, we have covered up to the momentum thickness. Now down one more thickness, kinetic energy thickness. How many of you know about this kinetic energy thickness? That will be sufficient. No, no doubt, the kinetic energy thickness. Till now, single time also it has not been asked. Kinetic energy thickness we denoted by delta double star. Uh, we know that what is the kinetic energy? Kinetic energy, we know that half of mass flow rate into U infinity square. When mass flow rate is being reduced, kinetic energy will also be getting reduced. There's no doubt about that. So here formula you just note down U by U infinity 1 minus U by U infinity whole square into dy from 0 to delta. Generally, we used to write 0 to infinity because delta to delta infinity, delta means C. In all the formula, whatever the formula we have discussed just till now, you will observe they have written 0 to infinity. Can we say it is directly equal to 0 to delta only? With very much confident. Why? Why? See, whenever we have the boundary layer formations, 0 to delta, we have this U by U infinity. But after that, delta to infinity, what is that? 0 to infinity can be written as 0 to delta plus delta to infinity. Delta to infinity, U by U infinity is always 1. 1 minus U by U infinity, always 0. So it's better you write either this or this. Both are having same meaning. Right? So here also the same thing, 0 to delta or 0 to infinity, whatever you can write, it's up to you guys. Now here note down one more term, safe factor. It's a ratio of displacement thickness to the momentum thickness. Displacement thickness to the momentum thickness. And why the name is given safe factor, not any other factor? Because displacement thickness and momentum thickness will depends on the velocity profile. What is the shape of that velocity profile? Because of that, the name is given as safe factor. Note number one. Put a note number two. Delta will be more than delta star, more than delta double star, more than theta. valid for all the velocity profile. It is valid for all the velocity profile. Note number 3. Whenever the fluid is flowing over any solid plate and we have the boundary layer formations like this, what are all the boundary conditions we have? Note down the boundary conditions. At y equal to 0, u is equal to 0. First. Second, at y equal to delta, u will be u infinity. Almost. Third one, at y equal to 0, at y equal to 0, tell me guys, what will happen with dou square u by dou y square? And note down fourth boundary condition, at y equal to delta, dou u by dou y will be 0. Here dou u by dou y is 0. Here it is maximum. At y equal to delta, at y equal to 0, dou u by dou y is maximum. If it is maximum, for maxima and minima, dou square u by dou y square has to be 0, according to mathematics. Getting my point, all of you? Understanding or not? Or you can also complete this third boundary condition from the Navier-Stokes equation. What is that? What is that Navier-Stokes equation? So here you can write rho into dou u by dou x plus v into dou u by dou y plus omega into dou u by dou z minus dou p by dou x plus mu dou x square plus dou square u by dou y square, like this. So now when you just do that, for the flow over the flat plate, dou p by dou x will be 0, because here, everywhere the pressure is what? P infinity, P infinity, P infinity. Now there is a no penetration, v will be 0. At y equal to 0, I'm asking at y equal to 0. This I'm applying at y equal to 0. Omega will be 0, steady flow. Then what will be there? Other conditions. What we can write? Dou u by dou x. What about dou u by dou x? At y equal to 0, what is u? 0, because of no slip condition. At y equal to 0, remember I'm applying Navier-Stokes equation at the wall where y equal to 0. Y equal to 0, u is equal to 0 because of no slip conditions. Getting my point? If dou u by dou x, see, u is 0 means what? U is 0 means what we can say about that other conditions. What about dou square u by dou x square, this term? Focus on these conditions. Now every term is gone. Dou square u by dou y square will exist. But what about dou square u by dou x square? At y equal to 0. Dou square u by dou x square at y equal to 0. What is the value? Yes, tell me guys. By order of magnitude analysis, what you can write? U infinity by something called L square. Now, as compared to delta, this L is very, very large quantity. So again, this term will be gone, right? This term will be gone. So you are left with only dou square u by dou y square, and that is equal to what? 0. From here also you will get, from mathematics or from the Navier-Stokes at y equal to 0, you will be getting the 4 boundary conditions. Among all, whenever in GATE exam, any question will come to get the velocity profile based on the boundary conditions. You have to use this third boundary condition. This is very, very important. Put a star mark. Whenever you have to choose between fourth boundary condition and the third boundary condition, you have to select third boundary conditions. That is more and more accurate. For the flow or the flat plate, pressure will always be what? P infinity. Because for the flow or the flat plate, this dou P by dou Y will be what? 0. When dou P by dou Y will be 0, whatever the P is there at the outside the boundary layer, that same P will be there inside the boundary layer. Understanding what I'm saying? Suppose there is a flat plate at this layer. Whatever the P is there, that will be same as P infinity. Here also, whatever the P is there, same will be P infinity. Right? Dou P by dou Y will be 0. Right? And flow over the flat plate means what? dP by dx will be 0. There will not be any pressure variation because all around we have P infinity, P infinity, P infinity. Understanding what I'm saying? Tell me, guys. Done. Can I move to the next one? Can I move to the next one? Now, understand the next particular concept I want to show you. See here, delta will be more than delta star, more than theta. That is what they have shown. This is the boundary layer thickness, which is obviously will be the larger one as compared to the delta star and as compared to what? This theta. Very quickly, just make a note of it. Whenever any curved surface is there and we have the boundary layer on that curved surface, and if you just write the y momentum equation, what is that y momentum equations? Rho into ay, u into dou v by dou x plus dou u by dou y, omega into dou v by dou z, plus body force in the y direction. But this boundary layer is a very narrow region, very, very narrow region. What is the weight of that fluid? Very, very small, negligibly 0, right? Negligibly 0. Now we are applying the boundary condition, a Navier-Stokes equation in the y direction, in y directions, in y direction. In the y direction, my dear friend, there is no acceleration also. See that here. What will be there? What we can write? Omega will be 0. What about v? What about v? V is a very, very small as compared to u, almost 0. If v is very, very small, dou v by dou x will also be very, very small. That is also 0. Right? Now, what about this term? Dou square v, if dou v by dou x is 0, then dou square v by dou x square, that is also being 0. What about dou square v by, see, v is a very, very small quantity. If you do any differentiation, that is also gone. So what you can write? Dou p by dou y will be 0. What is the meaning of that? Inside the boundary layer, whatever the pressure is there, outside the boundary layer, whatever the pressure will be there, exactly same. Outside, what is the boundary layer pressure? P infinity. Inside, it has to be P infinity then. Now, if we are having the P infinity, we can apply the Bernoulli equation to get the values of dou p by dou x. If you want dou p by dou x formula, you can get from the Bernoulli equation. What is the Bernoulli equation? P plus half of rho u square is equal to C, right? Can we write like this? U infinity square into like this. So if you want to get dp by dx plus half of rho into 2 u infinity du infinity by dx equal to 0. So what we can write? Dp by dx. Can we write minus rho into u infinity into du infinity by dx? Can we write like this? Check it out. Tell me, guys. Whatever the pressure is there, if I want to get the pressure value, I know that pressure inside and outside will be same. So if I differentiate just because of the Bernoulli equation, we can apply outside the boundary layer. Outside the boundary layer, we can apply like this. So in x momentum equation, whatever the dp by dx is there, how to get dp by dx? That is a very big headache for us. That can be sorted out very quickly by just differentiating these Bernoulli equations, and I will be getting dp by dx something like this. If it is a curved surface, my dear friend, if it is a curved surface like this, then we know that u infinity will be what? Start increasing, and then u infinity will be start decreasing, just like a car flow. You have a car, and say flow domain is there. In that case, dou p by dou x will not be equal to 0. But my dear friend, the flow over the flow over the flat plate, any changes will be there in the u infinity in x direction. If there is no changes in the u infinity, this will be gone, this will also be gone. And that's how we are getting here. That's what I have written for the flow over the flat plate, this term to be 0, so that we are getting this term exactly equal to 0. Getting my point? So it's a very deep discussion is there in Sinjal also. Either you can follow that, or you can just go through this in a very shorter way. Now, so all of it done with this. So what I'm just doing right now, I'm just giving you 15 minutes of break, 1 5 minute. 12:30 we will come back, or maybe 12:40 we will come back, and then we will see the next discussion on the boundary layer theory, and we will try to complete the dimensional analysis and similarity also. A very small chapter, but we can quickly we can finish that, right? Thank you all. We have the class at 12:40 or maybe 12:35. Please come back, right?